Thanks very much, Jesse. Sorry about that. I started sharing my screen before I'd unmuted myself. I really appreciate the introduction and appreciate everyone's attendance, and hope everyone enjoys this webinar where we'll be discussing modeling laboratory plasmas with the Flash code. Before we begin, I wanted to provide a brief overview of the Flash software, what kinds of capabilities it provides, and what are some applications that are of interest in sort of today's research environment. So Flash is a modular software for high energy density physics and also for astrophysical phenomenon. Its core solver routines consist of compressible flow solvers on a block structured mesh. It provides a 3-temperature representation of a single fluid. The 3-temperature representation permits the independent specification of electron, ion, and radiation temperatures. This is very useful for systems for which thermal or radiation properties are out of equilibrium with the plasma. This may be common because of some kind of heating mechanism or absorption mechanism which preferentially drives temperatures in one of these 3 populations as opposed to the others. The code also provides support for magnetohydrodynamics for modeling a diverse array of plasma systems, including magnetized plasmas and all sorts of other astrophysical or laboratory-based plasmas with strong magnetic field evolution. The code has support for adaptive mesh refinement, which enables the specification of a sort of high-level coarse block structure that can be refined as needed for pre-specified or user-specified variables dynamically during the simulation to reduce the total number of blocks in the simulation and optimize the computational efficiency. As far as additional physics support, the code provides a species-based characterization for state and transport models. So that means that things like resistivity, conduction, and other models describing heating and dissipation within the fluid can be described using very specific state-of-the-art models that are able to capture various idiosyncrasies of the plasma based on the species of the fluid. It also provides support for tabulated equations of state for accurate internal energy and ionization calculations, which can be updated dynamically during the simulation. It also provides a number of additional features that are specific to laboratory high energy density physics. This includes ray tracing and laser heating mechanisms for different kinds of ablation experiments or other kinds of laser interactions, as well as Thomson scattering and X-ray imaging diagnostics to help capture and emulate what diagnostics might see during a particular kind of experiment. The code is maintained by the Flash Center for Computational Science, which is located at the Rochester University, provides extensive documentation and a suite of robust test problems, which you can access once you go to the website and have access to the code. You will need to request access online, but that's a fairly straightforward process that you can do at the website. And just to highlight these sort of interesting examples here, moving from top right, this sort of top right animation illustrates what's known as a Rayleigh-Taylor unstable flame evolution. And this is actually one of the supply test problems of the code, so it's something you can go and explore for yourself. The basic idea is that if you have a region of low density, say partially burnt fuel, interfacing with a region of high density fuel, you may develop a Rayleigh-Taylor instability, which can lead to mixing of the fuel and flame interfaces, creating what's known as a deflagration. This is something that's of interest to astrophysicists studying supernovae, because they believe these kinds of deflagrations can lead to runaway conditions that may drive these supernovae in particular stars. It's also a problem of interest for people designing, for instance, rockets or other kinds of tiered fuel systems. The bottom right animation shows the results from a CDOF chamber simulation, which is also another test problem in Flash. And this one I'll go into a little more detail on in the demonstration, but the basic idea is you're driving a strong blast wave by depositing energy in a very small point and letting that blast wave expand into a domain which is filled with some kind of diffuse gas or fluid. Only in this case, we're introducing a fixed chamber with specific apertures for this blast wave to interact with and create, different kinds of turbulent flow and different kinds of distributions in the pressure and energy that system. So this might be a good analog for the kinds of experimental interactions where you might have a chamber that's either porous because you're using some kind of diagnostic, or because you're trying to understand the interaction of some high energy density response within this medium. And lastly, in the bottom left, we have an image from a very recent set of experiments undertaken to study turbulent dynamo mechanisms in laboratory generated plasmas. And so what we're seeing here is the result of plasmas, a plasma generated by streams of gas being filtered through these two specific devices held at a very short distance apart, which are then ignited by lasers coming in from either end of the domain. And the counterstreaming plasmas, coupled with the intense energy and magnetic field in the lasers, drives what is known as the Biermann battery mechanism, which helps to seed and amplify magnetic fields in the plasma. And it's believed that this process is responsible for the prevalence of very, very large magnetic fields at galactic scales throughout our universe. So this is one of a series of novel and sort of first observation experiments performed to study this mechanism in a laboratory environment. So this is the kind of interesting application that might be studied using the Flash code that really brings together a lot of the different features of the code itself. So how do we actually begin to think about constructing and running a Flash simulation? So I want to provide a couple bits of information about that before jumping into a demonstration. As I mentioned before, the Flash code is constructed of units, and those different units have essentially different responsibilities in constructing and operating the actual simulation. And those units are interoperable, so you don't need to necessarily include all of them in a given simulation. Some of these units may specify very particular physics, very particular diagnostics, or very particular IO capabilities that you may or may not need in every simulation. And so the aim of the user is to decide which of these capabilities are really necessary and to craft their executable in a way that is tailored to that application and maximizes the efficiency and runtime of that application. The code is also hierarchical, meaning you can include an entire unit in and of itself, or you can select from within subunits to sort of, again, further customize that executable and optimize its performance. Now, as you might imagine, this leads to quite a lot of decision making in the initial configuration and building process of the code. And so Flash provides a fairly structured operational procedure for building the executable, which I outlined right here. The first step in this process is the configuration process. And in this case, you're going to produce a series of files to sort of inform Flash what it's expecting and what kinds of hooks you might want as the user to build and operate the code. The first item is this config file, which will indicate the units that you'd like, as well as specific variables that you may want to use to describe your particular problem. The second set of files that you might want are what's called simulation files. And these are files that are used to describe the very particular and customized environment that you're describing for the simulation. So this includes user-specified variables, as well as initial conditions that are used to give your domain the particulars about density, temperature, other state quantities, as well as perhaps energy deposition or laser propagation features. And finally, there's also hooks through different routines to modify or adapt the simulation on an every cycle or sort of dynamic basis that permits you to include adaptive changes to the simulation. So for example, you could change something about some threshold in the simulation that will cause some dynamic to undergo, perhaps once you've met a certain threshold in the simulation. Once you've built this configuration, you have to run a series of commands to actually build the executable. And so this means first running setup, which is going to aggregate all the files and units that you need and link them and prepare them for actually building the executable. And then it will build the actual executable. Once you've done that, you can define a parameter file, and this is going to provide all the inputs for the runtime parameters specified by the simulation, Typically, these include those that you've already pre-specified in your config file, as well as others that may be natively provided by the code. And then you can run the simulation. The nice thing about this process is if you properly parameterize your configuration, then you're able to rerun the same executable simply by varying these runtime parameters and retain the exact same kind of performance that you might expect. So you can do parametric scans or other kinds of things using the same executable. But if you want to, say, just describe the problem differently or introduce a new kind of initial condition, then you're going to have to run back through this entire process and to build that new executable. So as you can imagine, this is kind of a fairly intensive process and often can benefit from a lot of expertise and guidance in building your simulation. And so this is where we've been putting some energy into the Sirepo interface to better enable users to characterize and build their own simulations. So with that said, I'm going to now switch to beginning this demonstration. So I'm going to stop sharing my browser for a moment here, or sorry, my PowerPoint for a moment, and switch to sharing my browser. Okay, so hopefully everyone can see my my browser window now. And where I am right now is at the sirepo.com/flash, this is where the Flash interface lives. And if you do go there, you'll be asked to provide credentials for the Flash Center. So you have to be an authorized user of the Flash code to access this interface. But if you do have those credentials, you should be able to enter them through a standard OAuth hook that should allow you to access this interface. And you'll begin at the simulations panel. And this is sort of your home directory for any kind of Sirepo-based simulation. So those of you who've used Sirepo before should find this fairly familiar. You have a number of immediately available options here. You can create your own new simulation. I'll bring up a modal here, which will allow you to do that. You can create or manipulate a new folder to help sort or otherwise organize the work that you're doing in this directory. For a given user, this kind of your home space here is persistent. So creating a folder and organizing runs for that folder might be something you might want to do if you're going to revisit this the interface pretty regularly. And then you also have capabilities to import files, which I'll discuss at the end of the webinar. So we're going to begin this demonstration by clicking on the examples folder. Everyone will have access to this folder when they first arrive at the interface. And the examples folder consists of a number of test problems from the provided by the Flash Center, so that come native with the code that we've gone ahead and configured for new users of the interface. And the one I'm going to demonstrate today, as I mentioned earlier, is the seat-off chamber simulation. So clicking on this seat-off chamber simulation brings us to a sort of very bare interface in what's called the setup tab. And so what's happening here is the interface is first going to extract the simulation files that come with this problem. So if you'll recall from my brief talk, the user must specify a configuration file along with a number of simulation files in order to completely describe their problem. And so these come by default with this particular example. And we're displaying them to the user in this panel. And if you want to, you can actually click view and take a look at the configuration file. You can see that it has a descriptive string here that notes it's a configuration file for a seat-off explosion problem. You can see what drivers are, what units are being required. And you can see some of the initial parameters that have been specified by the configuration to be expected by the code. So for example, this sim_p ambient variable is expected by the code. It's expected to be a user parameter, has a default value here of 10 to the minus 5 Pascal. And it has a descriptive or a doc string that tells you what it is, and that's this initial ambient pressure. And so we have similar parameters have been defined for density, explosion energy, coordinates, and so on. So these are kind of like setting the stage for this basic configuration. And these simulation files are going to take those parameters as well as other expected parameters and define them in a way that the code understands. So of course, you can also explore these files and download them as well if you want to look at them offline. Now that we have these files in place, we can actually run setup on this configuration. So I'm just going to run this default setup by clicking this button here, Start New Setup and Compile. While this is happening, I'll just sort of walk you through the setup arguments panel. So this panel is basically divided into multiple different components that are expected by this setup command. So these components include very common flags that are prescribed by Flash, specific to the grid geometry, which, as you note by this tooltip, will just tell you what's expected, what type of grid geometry. And you can see that you can select from a dropdown, in this case, between Cartesian, polar, cylindrical, and spherical. These are the geometries supported by the Flash code. You also have options to say, enable compiler optimization, change the dimensionality of the problem, introduce new species. Of course, if the configuration of the problem does not specify species, then you will run into an error, and the interface will deliver that error to you when you do actually run the setup and compile. And so as you walk through these different arguments, you have the opportunity to customize your setup command to incorporate the units and the capabilities that are specified in your configuration. And the way that Flash works, you don't have to include all of the necessary features in every setup and build process. You can ignore some of them, even if the configuration has some hooks that will enable you to use them in the future. And so that's just a way that you can keep the configuration flexible and build just the executable that you want without changing every single file every time. And this box right here shows you what that setup command will actually look like. So this is the command that would actually be run at the command line if you were, say, doing this outside of the interface. Once you've done this, you'll see a setup and compile completed successfully. You'll be able to view the setup log and compile log. Clicking on these buttons will just download a text file to your computer. And you'll also notice that now that we've completed the setup, many more tabs have been populated in the browser. And these tabs show you a number of different capabilities for the interface for parameterizing your simulation. So we'll walk through each of these one by one. The first is this source tab, and the source tab gives you some of the highest level and most immediately important parameters for you to adjust for your simulation. So this includes, very importantly, what we call the Flash simulation parameters. These are these user-specified parameters that are defined in the configuration file and then expected to be initialized and instantiated and initialized in the simulation files. And so this includes the explosion energy, which is described as sim_exp energy in the config, the number of subzones and cells for applying a 1D profile, the initial ambient pressure, the initial ambient density, and various other coordinates. So you can go ahead and make changes to these particular parameters, and you'll note that as you do that, this will be reflected in the par file that's being preserved for your simulation. So if I want to view this par file, I'll note that I just changed the explosion energy from 1 to 2, and that change was updated in this par file that the simulation is keeping track of. So any changes that I make in this interface will be populated backwards into the par file, so you have a consistent set of files to download, export, or view later. This grid panel here provides very high level control over the grid in Flash. So this is basically where all of the quantities of interest are being described and evolved. And it's also where you can specify things relating to the adaptive mesh refinement capabilities. AMR in Flash is controlled using this paramesh library. So clicking on this paramesh tab within the grid panel brings you to a number of parameters where you can specify things like the total number of initial blocks in the domain, the minimum and maximum refinement levels, as well as what refinement variables you might specify. Typically, for very basic simulations, things like density, pressure, and temperature are going to be very commonly chosen refinement variables. But you'll see that if you click on one of these dropdowns, you'll have the option to select from ones that the Flash code thinks are variables that it's keeping track of that you might want to use to define a new refinement criteria. So of course you can select temperature, save changes, and now the code will look at the temperature variable as well when making decisions about refinement. These refinement cutoffs and derefinement cutoffs are all in normalized coordinates. And so if you want to learn a little bit more about that, I would encourage you to actually take a look at the Flash Users Guide, because they define the normalizations that are being provided here and how to think about these different items. And what you want to set those parameters to is going to change a lot depending upon what system you're running on and what your interests are in resolving different kinds of features. So now that we've run through this source panel, we're going to jump into the physics panel. And the physics panel here is going to aggregate all the different physics units that the code is included in the configuration. So in this case, our configuration was very simple. We only requested this hydrodynamics unit, and that's all we're going to see in this panel. And we have a number of very basic parameters for this the hydro unit that we can specify. This includes things like the CFL factor, which is basically a time step multiplier that's applied to make sure that the simulation evolves the fluid stably. And so typically your selection of this CFL factor will have some default value, but you can modify it as you see fit if, say, you're running into a very diffusive simulation, or if you're running into a problem where the velocity accelerates dramatically and you want to just be very careful about the time step in your simulation. You can also make specific choices about things like artificial viscosity, what kind of Riemann solver you're using. So if you do have a particularly diffusive simulation, or if you're running an MHD simulation where, say, the HLC solver is more effective, then you can make those changes within the interface as well. So now that we've specified our hydro units, you can then move to this runtime parameters tab. And this is basically a directory in which you can search and evaluate all of the possible runtime parameters for your configuration. So this has been populated by all the things that Flash recognizes as feasible runtime parameters, but in an indexed way and not in a sort of formatted way as presented in these other tabs. And so that allows you to, say, search for something that you weren't sure about that you really wanted to understand. So if I wanted to understand something about the EOS, I could search for a very particular EOS variable. I get a reduced selection to click on, and maybe I think, oh, maybe the variable I'm looking for is under physics EOS. I can click on this, and you can see the different kinds of parameters that are available for your selection. And as with the other panels, you'll see you have the tooltips where pre-configured doc strings are provided for the user. And just as with the previous interface as well, if you do want to make a change, you can make that change, save the change, and it will populate backwards so that the par file updates just as it would with any other change to the interface. So now that I've parameterized my simulation, I have created an executable, and I'm comfortable with what I want to do, I can then proceed to this visualization tab. And the visualization tab is where we're going to actually execute the simulation and see the results. And so what I have here is basically a small panel that describes the simulation driver capabilities. And the simulation driver capabilities will define the sort of high level advancement of the simulation, including the maximum time, the initial time step, the maximum number of time steps, and this plot file interval time. And I want to highlight this one in particular because the plot file interval time is basically the frequency with which Flash will output specialized files which are lightweight and easier to use for visualizing specific variables within the code. So Flash has an internal designation for what's called plot variables, or plot underscore var. And those are the variables that the code keeps track of and will spit out to these plot files separately from checkpoint files. So the code has the ability to checkpoint itself. And when you do checkpoint the code, you'll get everything that was produced by the code. That will all be generated in those checkpoint files, so you can run a restart or you can evaluate every little aspect of the code. But you may not want to print out a checkpoint file every time you want to say, look at the density of the fluid in your simulation. So the plot files are generated in order to provide selective, lightweight outputs for you to analyze further. And so the plot files are what we're going to be using to produce and view visualizations in the interface. And so varying this plot file time is going to give you, say, a better temporal resolution into the dynamics of your simulation. So now that you specified all of these different parameters, you can go to the simulation status panel and you can actually start your new simulation. I will note that there are different run modes that are available within Sirepo, but these include support for running at NERSC. Depending upon what your level of Sirepo access is, you will have access to longer run times and potentially more cores. In this case, I'm just running with the basic execution mode that was provided. And you'll see that as the code runs, it begins to generate new panels that have visualizations of the domain. And so I can scroll down and take a look at what's happening here. And I really want to highlight each of these panels, which will be updating dynamically as the simulation runs. But I will actually move to a new tab where I have a completed version of the simulation to show you what it actually looks like once I've described these. So this grid quantity evolution panel is taking a look at the global quantities in the domain as they are evolving. So in this case, for instance, we're looking at momenta in X and Y, as well as kinetic energy in the domain. So if you're introducing some kind of dynamics that will generate a lot more energy in the domain, you can sort of see what happens there. Similarly with momentum and mass and other global quantities tracked by Flash. This 1D profile plot will show you the density or some other parameter of interest along one of the axes in the simulation at different times of interest. So this is a way for you to evaluate simple 1D profiles in the simulation. And this variable plot panel enables you to take a look at plot variables of interest in a 2D representation through a cross-section of the domain as the simulation evolves or after the simulation is completed. And so let's jump into this pre-completed simulation just to highlight a little bit of what that might look like. So you'll see that this simulation completed with 70 animation frames after about 14 minutes. And we have much more interesting profiles and grid quantity evolutions and variable plots to take a look at as a result. So here I'm looking at the density of fluid in the domain. You'll see a number of different options if I click on this pencil icon for characterizing the simulation. I can change the extent of the color map. I can change how what kind of plot is being generated. I can change the number of frames that are being produced per second if I want to actually play through all of the images. I can also visualize the grid underneath the simulation so I can see where the code is decided to refine based on the conditions defined in the setup. And then I can also modify the color map if I want to use a different color map. So here I selected a new color map and I added the AMR grid on top of the plot. And that's going to ask the interface to reproduce this plot. And you can see now a totally different color map, as well as all of these white lines overlaying the plot, which demonstrate the variations in resolution that the code has determined are necessary to resolve the dynamics of interest. I can step back through different plots here by clicking this button down below, and that will load different steps in the simulation. So if I take one step back, I'll see what's happening 1 millisecond earlier in the simulation. And to make this a little bit faster, I'm just going to turn off the AMR grid, which adds a little extra operation here on the plot. And I'm going to go all the way back probably all the way back to the beginning, just to show some initial evolution. So if you see these two buttons on the left and right, the sort of rewind and fast forward buttons here, those will go all the way to the beginning or to the end of the simulation. So if I click this, I return to the initial one. And then if I want to just let the interface provide every single plot for me, I can hit play, and the interface will just begin to show the full evolution of the simulation. These images are cached by the browser. So depending upon the browser settings and how recently you've loaded all these images, you will get different kind of latencies in the generation of these images. But generally speaking, it's fairly quick to sort of run through. I've already gone through 38 plots here. And once you've run through them at least once recently, you should see that many of them are persistent in the browser thereafter. So this sort of gives you I think a pretty thorough overview of how to actually run one of these examples, what kinds of capabilities you might expect, and what kinds of features are supported by the interface to evaluate and analyze your simulation. But what about creating your own simulation? So I want to briefly demonstrate for you how to actually create your own simulation and what that looks like in the interface. So I'm going to return to this previous tab here. While I'm at it, actually, I should note that there is actually a nice feature in Sirepo that will show you what jobs you have currently running. So I started this seed off chamber run a little bit ago, close to 12:30, and I can see a status in this jobs tab here that will show me exactly what's going on with the simulation. And if I want to, I can end the simulation. I don't have to be in this tab. I could have been looking at the other simulation and I could still end that from that jobs panel. So I'm now going to go to simulations, back to the simulations tab, and I'm going to create a new simulation. I'm going to put it in the webinar folder, and I'm going to call it new capillary discharge. This is going to be a simulation of a capillary discharge plasma, which is something that we've done some work on at Radiosoft in support of the accelerator community. And you'll find here that now there's no pre-existing set of problem files to extract. I have to specify them myself. And so what that means is you have to create a zip archive that has, at its highest level, all the different problem files that you want to include in the simulation. So I can upload a new file from my desktop, but in this case, I've already pre-uploaded a zip file, and Sirepo will keep track of that. So we'll say, oh, you have this Sirepo config.zip that you've uploaded previously. Do you want to use that to create a new simulation? So I'll say yes. And the interface is going to extract these new simulation files and produce a new setup tab for me. And this will take 10 or 15 seconds. So we can see that this new configuration has a number of additional files that didn't exist before. And I can talk a little bit about that once I start this setup. So I just want to add a couple specific items to this setup argument. And you'll see that as I save these commands, the setup argument's being modified in real time. So I'm just going to add all the different features that I want in this setup and make all of the necessary adjustments to the parameterizations for these feature flags. And as I do that, the setup command becomes more and more dynamic. And now I can hit start new setup and compile. And that should build this new executable with the files and with the capabilities that I've specified in the setup command. And I can return to something that's a little interesting and different about this setup. So you'll notice that in addition to the simulation files, the config file and the par file, there's a number of other Fortran files that have been uploaded. This includes, for instance, this magnetic resistivity full state, this grid BC applied to region specialized at F90. These are files that the Flash code provides to users, but which have very default capabilities. And some simulations may warrant specialization. And so you can always include a very specific file that you want to overwrite or overload, say, a specific function in that Flash executable in your problem file setup. And the code will copy this version into your build directory, and that will basically replace the previous default version of the code. Similarly, you can add additional external files that the code may read in. And this could be a DAT file, this could be a .cn4 file or an ion mix file, which describes an EOS. So there's a lot of different things that could be specified here. And now that setup and compile is completed for this new example, I can again look through these different tabs. And because this setup was a little bit more complicated, not only do I see substantially more options in this simulation parameter panel, I also see a number of new panels in general. And that includes, for instance, this multi-species panel, which allows me to describe the different species. These have been pre-populated with atomic numbers based on what the config file expects. So I don't necessarily have to make changes to these, but it does show you sort of what you're trying to use here. You can also see in the physics tab that because I specified adding the laser, because I specified adding radiative transfer or multi-group diffusion, and because I specified different other material properties, these are now included in the setup as well. So as a result, this simulation has gotten a lot more complicated than the previous test problem that I demonstrated. And it's situations like these where this runtime parameter index and sort of search features can be rather valuable, because you may not know where to go to find the specific parameter of interest, but this helps you provides you with at least a little bit of an easier way of searching for a very specific parameter for your simulation. Nothing will have changed about the visualization panel, though. That's consistent across all of these configurations. So with that, that completes my demonstration of the interface, and I welcome any questions. Thank you very much for your attention.
All right, thanks, Nathan. That was great. I really appreciate your work that you put into this. We do have a couple questions lined up, and I would encourage any other folks to put their questions in the Q&A at the bottom of the screen. First question we have queued up is it possible to download the visualizations or the other results from those simulations?
Yes. Okay, let me walk back over to this CDOF file. So up here, I omitted to talk about it, but you can specify. You see this little download button. I can download these images directly as PNGs with varying compression. I can also download the raw data file. And so that will open up a little tab, sorry, just to process the download. But that will actually download the H5 file from the simulation. So Flash uses HDF5 for its outputs. And so you can download the actual data files from a given step, the actual plot files, I should say, not the checkpoint files, from an actual step that corresponds to the image that you're looking at. In the case of this grid quantity evolution, because these are specialized global quantities, the actual file that you download is not an H5 file. It's this .dat file, and that's persistent through the entire simulation. So it's a little bit different from the H5 download here.
Awesome, thank you. I have another question queued up here. I'm going to read it out loud for everyone, but I've also sent this to you in a direct chat, Nathan, so you can see it, because I'm not sure I'll be saying everything correctly. It says, I am currently using Propaceos EOS with Flash, which requires a patch to let Flash use the .prp files instead of the ion mix files. Will Sirepo support these different EOS tables in the future?
That's a great question. Yeah, so I think there are plans to support Propaceos EOS within this interface. Currently, the patch is not part of the build that we're supporting in our container. So I think that's still an open issue, but it is one that we hope to provide support for in the near future. For now, the code will support any ion mix formatted file that you upload. So if you have a ion mix variant of a table that you've constructed, you can still upload that to augment your own simulations.
Excellent, thank you. So I have our last question that we're probably going to have time for since we're a bit long already today. So the last question we'll address is, how do I force a region to be fixed, like the chamber walls in the simulation?
Yes, so yeah, so this is a very commonly asked question from Flash users. Flash is a fluid code, so everything in the domain is treated like a fluid, which means it will respond thermodynamically and hydrodynamically to what's happening around it. But there is a special feature called boundary var, which is basically a flag that you can set for different regions where you will fix the fluxes in that region. So if you want to make a immovable region in the code, you can set that boundary var flag for that particular region. And that requires you to edit the simulation init block and potentially some other files, as well as in your configuration, to define the specific portion of the simulation domain, which will be treated as fixed. That's also something, though, that you can change as the simulation proceeds. So if you do want to permit the boundary regions to move after a certain time, you can adjust your simulation by modifying the simulation adjust evolution file, for example, to permit that boundary region to begin to flow like a typical fluid.
Lovely. Thank you very much, Nathan. I appreciate that. So we are just at the edge of our time boundary today, so we're going to sign off from this webinar, but thank you to everyone for coming. I will make one last point that Flash is our very newest app in the Sirepo family, so I will put a direct link into the chat so you folks can access that. It will be coming to a link through our webpage later this week. If you have any further questions, we would love to help you with those. We would encourage you to use our Slack workspace to access us and ask us those questions. And I'm going to also link that to you in the chat here. So feel free to join our workspace. That's the easiest way to get a hold of us. And we will be sending you guys a follow-up email in a few days that has the link to the recording for this webinar. Please join us in August for Dr. Boaz Nash and our next webinar in the series. Thanks, everybody.